Hello, everybody. My name is Dragutin Petkovic. This is a part 2 of our lecture on AI explainability, and we are going to talk about SF state algorithm for improving explainability of random forests. I'm going to share the screen now and actually pop up the slides that I will actually start showing now. So this is part 2. Remember, we spoke in part 1 about explainability in general, its motivation, importance, and how is it done. And we overviewed LIME, a state-of-the-art, very well referenced explainability method. Now we are going to talk about our own method in my research group. So pardon me if you see some bias. I'm going to try to kind of objectively lay out what we do and some advantages and disadvantages of our approach. And I will give you references, and I welcome your feedback through Professor Zicari. And hopefully you can even use it for your own research. That would be wonderful. So this is work with me and my graduate students from SF State, Ali Alavi, Dandan Kai, Sabiha Barlaskar, and Jizu Yang. And work is partially supported by an NIH grant, sub-grant with Stanford University, and our mentor, Professor Russ Altman, and by SFSU Cozy Computing for Life Sciences Center. These are some publications and even a YouTube tutorial with some test database and Jupyter Notebook toolkit for RFX. So you can try it yourself, and I will explain you how you can use it. But I'm not sure whether all of you know random forest. I can't ask you. So I'm going to quickly overview it. It's invented year 2001 at Berkeley. It's a classical ensemble tree method, extremely powerful, accurate, well-documented, state-of-the-art. And I can tell you, honestly, today, everybody is enamored with deep learning, and of course it's good. But I have to tell you, in many competitions, random forest does equally well as long as the data is of the format that random forest can digest, which means more structured, independent features. But it also has built-in innate explainability, which we leverage in our work. So it's one of the most powerful and widely used. It uses number of slightly different decision trees on purpose made slightly different, who then vote together for deciding on the class. Each tree incorporates well-known card decision tree algorithm to grow each tree without pruning, but with a clever trick, it doesn't try all the features, only a random subset of all the features in each node. So that makes it that each trees are slightly more different, they're more noisy, but then by working together, it kind of balances out. Invented at UC Berkeley by Professor Breman, and it's best for problems where the features are structured in typical feature vectors where there is not much time on spatial relationship between features. It can use numerical and categorical features, deals very with useless features, it ignores them, and with missing values. And it's very fast and inefficient. Being a collection of trees, it has inherent explainability, okay? So basically it uses collection forest of trees, which is done by parameter called N3, number of trees. Each tree is designed slightly differently on a bootstrap database of original data. So original data, if I have 1,000 trees, we create 1,000 slightly different bootstrap training sets by random extraction of data from original database with replacement, which causes about 36% of the data to repeat, which means that each tree in the forest does not see about 36% of the data. And therefore, random forest has built-in cross-validation. In other words, each tree is trained on slightly different set of data. In built-in error estimate, which is called out-of-bag error, each tree is tested only on the trees it did not use for training. So you don't need to use actually cross-validation. It's very powerful. The trees vote, and you can adjust the voting threshold. And this, we will come to that. It's very important. And that voting threshold actually can control the sensitivity between false alarm, false positives, false negatives, okay? So a random forest actually offers critically important measures of feature ranking. Gini-based, which actually looks at for each feature on average impurity, it influences in all the trees, and the one that's most commonly used, mean decrease in accuracy, excuse me, which is, again, if you recall the part one, a form of sensitivity analysis. Each feature value is randomly modified one at a time, and the tree is tested again with all the samples, and we record the drop in accuracy over all trees, okay? And then when we repeat it for all the features, we rank them by the features that cause biggest drop in accuracy. And mind you, in our group, we use it a lot. This rank of feature can be applied separately for samples of positive and negative class, which in many cases, in cases where your database, training database is imbalanced, which is commonly the case where there are many more negative or background samples than positive, the features critical in deciding on positive class could be different from features for negative. So in that case, we recommend you use different MDA. Both Scikit and R provide some of these measures. Scikit provides only Gini. R toolkit provides both, including class-specific MDA, okay? So these measures we leverage in the heart of our algorithm. So how do others use RF? How do others actually explain the work of random forest? Two key approaches. The standard that you already saw, we simply ranking the features. To our actually surprise, I think people have enough compute power that they simply rank the features and use all of them. You will see that we emphasize and leverage the fact that usually the rank of feature, the power of their predictive power measured by MDA drop pretty fast after top few percent of features. And we will leverage that in reducing the dimension of the problem. Another way is to basically transform each branch of the tree into a set of rules. Now remember, you have thousands of trees. Each tree has many branches, so you have tens of thousands of rules. Each of these trees branches can be, like in this simple case, condensed into set of if-then rules. So there is a bunch of papers where actually they try to convert a trained random forest with hundreds of thousands of tree branches into a smaller set of rules. Smaller is this obtained by some optimization of sparse set of rules, which ends up having about hundreds of rules, each of them actually having a number of 5, 6, 7, 10 if-then else statements, which is not that easy to explain. And these are some of the papers that relate to that. So I'm now going to talk about our work, which we call Random Forest Explainability, RFX. And we are now at 2.0. We improved it from original paper published in 2018. Our latest paper, not peer-reviewed, is published in bioRxiv on this link, and the technical report is published here, which includes the YouTube video and the toolkit, okay? The key features of random forest, it has both model and sample explainability, which are integrated and is designed in the user-centric way. In this presentation, I'm going to demonstrate it on a large data set provided to us by Craig Venter Institute in La Jolla, which actually contained a ground truth, which is critical for our actually research. We actually had a ground truth biologically formed, which means it's really independent ground truth. So the goals of our work were simply, in this case study, was as follows. Can we, first of all, we would apply our model. RFX has both model and sampler explainer. Remember, model explainer will attempt to summarize how RF works on totality of the data, the whole training database. Can we then correlate the model with some of the ground truth independently established by biological analysis? And that would be good. Secondly, can we use RF sample explainer, which is the new work just recently finished, to identify samples and features of that samples that are possibly outliers or pathological, out of range, and problematic, which is essential for further analysis. Possibly could be a noise in the data or some new patterns, or simply to clean the database before you apply it for further analysis, which also Craig Venter people headed by Professor Robert Dare actually attempted to do. Okay, I'll give you these references. The work at Craig Venter was led by Dr. Robert Shorman and Bill Averman, and they published two major papers. In this paper, they looked at certain types of cells in neural cells, and they tried to identify certain clusters or types of cells, and consequently identify what genes turn on or off to create those cells. So their database contained of 608 features. Each feature is level of excitation of the gene measured by RMS samples from each cell. In other words, with using special biological equipment, they were able to look at level of mRNAs in each cell and use that as a numerical feature for each gene, where high level means the gene is expressed and a low mean it's suppressed. The database also as a feature, or as the classes for the classifier, contains 16 different classes for 16 different cell types. In this case study, we will talk about one cell type. In our paper, we analyzed 3 out of 16 cell types. So again, this is a typical database good for random forest classification. 608 kind of independent features, expression of 608 genes with well-defined classes established by ground truth. So the training database was reasonably balanced or not unbalanced. In our case, the E1 cluster that we try to analyze contained 299 positive samples and 572 negative samples, which we obtained from Craig Venter Institute. The background of this data and how it was discovered is presented in this paper. So our thing now, let's go further, okay? In trying to develop RFX, we try to answer a number of usability questions as they refer to the questions on explainability posed by non-experts, such as, for the model, some basic questions quoted in most of the literature. The most simple one is, which features contribute to the decision, okay? It's a very basic one. And can we rank them? Similar was with image patches. In our case, is which genes mostly contribute to indicating or creating certain cells. But then there are a bit more complex questions that users wanted to ask. What is the trade-off? This is one of the key. The trade-off between using subset of features and related accuracy. In other words, what is the accuracy if I take these 5 features? Or what is the accuracy if I take only top 5 ranked features? That's the common questions a practitioner would want to have. Because remember, although computing power is almost free, extraction of features is not free, and everybody would like to do the AI job with minimum number of features that can go away. The fourth question, besides this one, the fourth question commonly asked by people, okay, you ranked features independently one by one. What groups of features work well together? Are there pairs or triplets of features that together explain something or classify something? And naturally, people wanted to know the basic statistics and ranges of features for positive and negative class. Sounds very simple for ML experts, and certainly doesn't work if features are correlated, but a very basic thing that non-experts want to know is what is the range of values for class of positive and negative class for each feature. Very basic questions, often neglected in a work of ML experts. In terms of sample-based explainability questions, naturally, why was my sample classified correctly or incorrectly? Even if it's correctly classified, you want to know why, which is kind of what Lime tries to answer. Which features or factors contributed to incorrect classification of my sample? That's a very common question because your trust is in question. The first question you want to know, okay, why was it classified incorrectly? What feature is out of bound? And a very important question for curating and QAing the training database is cleaning them from outliers. How can I easily identify outliers among the data samples? What even is the meaning of the outliers? So let's look at a slide I created for my general talk to medical profession, but I hope you will find it useful. Maybe too simple, but I'm trying to create explainability technology that maps the outputs to familiar formats to practitioners. We are doing a lot of health applications. What is the most common format in health application? Is set of tests with ranges for sick, healthy patient and kind of the gray zone. Very basic stuff. Of course, it assumes uncorrelated features and stuff. But in feature engineering, as you know, we are really trying to use the set that's uncorrelated, that random forests will actually prefer as most important features that are uncorrelated and work well on their own. So look at the format. It's basic tabular format. And basically when you, let's say, take the blood test, these ranges are model of a general population. They basically tell you for most population, and they're usually not gender, sometimes gender specific, sometimes ethnically specific. But for totality of the database, these are the ranges of these features. These are features or tests and proper ranges. This is your model explanation of population based on these measurements. The sample test is done when the patient comes. The doctor would overlay patient results over the model, which simply says, where does patient data fit within the population model? And it will tell you, aha, this is the feature that really is out of bound. We have to investigate more. So this is exactly how we model our RFX approach. RFX has several steps. The first basic step is the standard training of random forest classification, where we compute accuracy, and we prefer F-score, which is combination of precision and recall in one number. We also use OOB, and we show confusion matrices, and we train it over the range of parameters of number of trees, number of features used for each node, and the cutoff. This is standard, okay? And we create a forest, a trained optimal random forest classifier. Model explainer is then created by using statistics of the training data and processing the model to create a summary table that's modeled by this table here with list of features and certain parameters. The sample explainer is then created from model explainer and sample data, again in the tabular format related to model, telling us where does this sample lay in the model explanation of random forest, and trying to tell us are certain features out of bound or not. These tabular formats are designed to be easily interpretable by humans who are non-experts in machine learning. That's the key property of random forest explainer. And I will talk more about our usability study on that. So both model and sample explainers are actually pipeline of steps that can easily be applied manually or can be automated technology like Jupyter Notebook, okay? So there are a number of steps in each model, and let's look at that in more details. The first step is running the actually standard random forest classification. And what we did, okay, was basically compute the accuracy in predicted E1 cluster. Let me just go back to E1 cluster and explain you again. Our goal was to show that our model can easily explain the ground truth obtained biologically, which says that E1 cluster of cells is defined as a middle temporal gyrus cortical layer, which I don't know exactly what it is, but it is created by selectively expressing genes type TESPA1, link 507, and SLC17A7, and suppressing the gene KNCP1. Mind you, these are the features among these 608 features. Each of these genes in the feature set has a number related to expression. It's high if the gene is expressed and low if it is not expressed. So this is our ground truth. So let's look now what our model will predict. So let me just show you our model, and then I will explain it based on this model here. So this is the RFX model explainer. What does it have? My slides contain the details. I prefer to talk to the result here. It's much more fun, and you can see in our paper exact description. So first of all, we are going to rank 608 features by MDA, mean decrease in accuracy, provided by a random forest. This is the value of it, and this is the names of features ranked by importance, okay? The next layer is the innovative measure that we pioneered, which we called cumulative F-score. F-score here is obtained by retraining random forest only on top 2. This one by retraining random forest on top 3. So basically, this number tells you what is the accuracy I can get by retraining using random forest only using this and all of the features above in the rank order, okay? So you can see that the ultimate accuracy was 0.995 using 608 features. You can see that using only 5 out of 600 features, I'm reaching 0.98, almost few percent loss in accuracy with over 95% reduction in the features. That is impressive, I would say, but it also repeats for all the applications we did. Usually the top 5% carries most of the work, okay? So not only that, but remember, the ground truth said that the E1 cluster is indicated by expression of TESPA, link C507, and SLC17A7. exactly the top 3 rank features in our model. So our explanation works. It correlates with what biological explanation is. And suppression of gene KNCP1, which is ranked 5th. Link C508 is version of 507. Now, how do we know even more that we are correct? These columns here are simple statistics of each of these features. Basically, from training data, we compute average standard deviation, mean and max over 299 positive samples and 587 or 578 negative samples. So let's look at that. High expression of TESPA1, Link C, and SLC. High, low, high, low, high, low. High for positive class, low for negative. Very correlated with biological ground truth. KNCP1, low expression. Positive data, low. Negative data, very high. Look at the average. So it's perfect explanation of the ground truth obtained by different means. So RFX model in one page, and our rule was the whole explanation has to be done on one page because of user interface and simplicity. Tabular format, one page. You have feature statistic, you have ranking, you have cumulative score. So now you can say, I have budget to measure only 7 features. What can I get with it? Well, with only 7, you can get almost as good accuracy, so you're good. You save a lot of money, okay? The last 2 columns are also interesting. We use Cohen distance, which is simply difference between averages normalized by standard deviation, and Cohen distance is better than p-value in determining differences in distribution, but because it gives you some measure, and anything above 0.8 is considered very good separation. So indeed, this model tells you that we got high F score. Obviously, this was easy set to classify, but the good thing is that the model completely confirmed the biological ground truth. The last thing is very important. Now that I have only 8 features to play with, I can do all sorts of exhaustive searches. I can produce the clique of features. In other words, I can do exhaustive search of 8, choose 3, and look at all combinations of 3 features from set of 8, which is around 100 or less, and apply random forest separately to each because it's efficient, and rank them and look at the top 10 groups of 3. Know that they're not necessarily 1, 2, 3. And the indicative from this, thanks to our colleagues from Craig Venter Institute, they noticed that the gene TBR1 mysteriously appears in a lot of cliques. So they told us, to my delight, oh, look at that. Why is this gene so predictive here and appearing in all rankings? We need to look at it. Maybe it's important. In other words, by looking at the explainability report, you can observe certain factors and patterns in the grouping of features that bring new knowledge. And that's kind of the ultimate win. Now, this is now the again explanational model summary confirming the model and the new gene. So some discussion, as we said, that we observed the perfect ranking in the model, and the model was basically easy to use. That was really important. One-page tabular format. But some of the novelties in the models were that we provide trade-off of explainability and accuracy by this cumulative F score. And also we are providing a list of features that work well together. Nobody is doing that, and we can do it because now we have only 8 features describing the whole process with almost as good accuracy as all features. The top accuracy is 995, top 8 features bring us to 0.9917. So now we can even extract the cliques of 3, cliques of 4, and do all sorts of analysis. And everything is done in the format familiar to, let's say, biological researchers, non-machine learning experts, tabular format on one page. So we believe that it's really useful. In our work of 2018 that we published in this reference, we even did the usability study of RFX and notice and prove that it actually builds user trust. Notice that we investigated 13 users total, but they did a self-survey and we grouped them into feature is the domain. It's the application we analyzed from Stanford. These are non-experts in domain, non-experts in RF, all the way to experts in domain and experts in RF. The score 1 to 5, 5 being the best, indicated improve of the confidence in classification after they were shown RFX summary. So initially they were shown only F score, which is standard way of describing accuracy of classification, and they rated their trust. After that, we showed them the full explainability model report at that time, and they ranked the increase in trust. And looked at the increase in trust, especially for experts, and here also experts in domain and non-experts in machine vision was considerable. And we believe that we achieve some improvement here. It's a modest test with only 13 users, but unfortunately, I saw only few papers, including Lime, folks who actually have attempted to test their explainability with real users. Most people do not. And we think that has to be part of our toolbox and evaluation criteria, okay? So think of any questions here and think how would you like this kind of format where you have list of features, name, cumulative score, some sense of ranking, the idea about statistics over positive, negative samples, and an ability to get some idea about which groups of features work together. That is model explainer, and it's limited to 1 page only, okay? So now let's talk about sample explainer. As we said, most people will build their trust in machine learning by keeping their own samples separately and testing them on the system that you provide them. Basically, independent test on the samples, on the patients I know very well. Show me what you can do. And that's proven in the paper I quoted before to be critical in building user trust. We created a sample explainer where, of course, the first thing you want to know whether sample is correctly classified or not. But the novel measure we used, which to our surprise nobody uses, is how many trees, the fraction of entries voting correctly for this sample. That's such a simple measure, and we'll show you that it correlates well with accuracy in classification. So it's yet another confidence measure. And in this era of politics, we can complain it to elections. Has the candidate won with landslide or barely won with 51%? Basically, did you win by 90% of trees voting for you, or only few trees above the cutoff, like 51%? So the sample can be identified as problematic outlier, of course, if it's incorrectly classified, but also you can look how close was it to cutoff voting. If your cutoff for voting was 30%, if sample was voted correctly with 31%, we can still say, oh, maybe it deserves some more scrutiny. And the model classifier relates to actually, the sample classifier shown in this table relates to model classifier. It's kind of the similar format. Let's look at it. This is the model classifier. These first 3-4 columns are the same to give you a reference, like in medical test. This is again the top ranked features from the model, the MDA and the ranges for positive, negative class. And now this is the value of test sample. So we can relate its own feature value for each feature in relationship to the ensemble or statistic from the training data and few other measures. Basically, we show the feature value and we are looking at its coincidence or normalized distance, difference between feature value and average of the sample population for a positive and negative class divided by the variance. And again, if the number is anything above 0.8, it's considered very less than 0.8 in this case is considered close. And look at the top ranked features. They're very far from negative class, very close to positive class. That builds our confidence, right? And same here, very close to correct class and much farther to other class. Additional non-parametric measure we use is for each feature, we look at 30% of positive class, that's our threshold. The neighbors in that vicinity was, and that was 60. Out of 60 neighbors around this feature value, how many were of the correct class? It was 57. In other words, the sample is within the neighborhood of samples of similar class. That gives you some idea of whether it's outlier or not. And this is done for each feature separately. So in this case, all of these features satisfy the simple intuitive rules. Their values for each features are closer to the correct class than the incorrect class, and most of their neighbors are of the correct class. So this is the sample where actually you will see it here. This is the sample where 100% of the trees voted correctly for it, and all features are, we call it in the range. They are obeying certain good rules, that their averages are closer to correct class than incorrect class, and their neighbors are with high majority of the correct class. Let's look at the correctly classified sample, which we deem problematic, which was actually received the lowest fraction of vote, only 80%. Okay, very few samples in this cluster of E1, which was easy to classify, received the lower voting threshold, which means only 80% of trees voted for that. For us, it's potentially problematic. Maybe yes, maybe no, but deserves more scrutiny. So let's look at it. Green means good, red means potentially problematic. TESPA 1, the key feature, again, very close to correct class, very far for incorrect class, all of the neighbors correctly. So this feature being most important really was key for this sample. But all the others actually, and CP1 also did very well. Most samples correct class, closer to correct than incorrect class. But the features ranked 2 and 3 were not. The feature 2 was closer to incorrect class than correct class. The coincidence was smaller to negative class. Same with feature rank number 3, and they had only few samples in their vicinity, which means that these features are causing the low number of votes. So it could be due to many reasons, and people from Craig Venter are investigating. Could be that it was error in the measurements, and that happens. So maybe we have to delete this sample from the training data. Maybe not. I don't know. This is biologically has to be checked, but at least the RFX model and sample, especially the sample, can indicate the samples and the features that deserve more scrutiny and identify which features cause this low threshold. So voting threshold is the first indicator, and then the rules, which means the feature is out of range if coincidence, in this case to correct or positive class, is bigger, it's farther from positive to negative class, or the number of neighbors in its vicinity is less than 50% of correct class. This is kind of a simple intuitive rule we use to identify potential outlier features which could be real data or noisy data due to noisy measurements. So I'm here having some discussion. What would you do with RFX if features are categorical? You would have to then list actually the features and not just use the coin measure. And there are some ways to actually address it. And if RFX is used for regression, again, instead of cumulative score, you can use RMS score, but still provide some sense of what combination of or top use of top rank features, what is the ultimate accuracy you can get. So if we compare RFX and Lime, some things are obvious. RFX is specific to random forest, Lime is agnostic. RFX is direct. It explains random forest using random forest, because for each of these experiments in obtaining the values in the explanation tables, I retrain the actual random forest classifier, okay? Lime is indirect. It uses linear classifier to approximate unknown black box. RFX has both global and local model or sample explainer. Lime is inherently local explainer and has a variations where you can use a lot of samples to try to find the rules that hold across the model, okay? But it is a bit more complex analysis. RFX offer trade-offs between accuracy and subset of features used, which is actually provided here. If I use only certain number of features, this is the ultimate score I can get. Sorry for going back. This is your cumulative F score. No other explainer that we know provides this, okay? And this is very important for practitioners. It's quoted as one of the explainability requirements people have. RFX, for ease of use, has familiar tabular formats and also provides feature statistics, which is the basic things non-practitioners wants to know. Finally, RFX offers information about most descriptive or discriminatory groups of features by actually using RF. So these triplets of features are actually correctly estimated. They're not estimated by approximations. They're estimated by retraining random forests to each group combinatorially, because from actually having only 10 or so features in the model, we can actually provide all of this information by using exhaustive search. So these groups of features were done by retraining random forest on each combination of 3 choose 8, okay, which is actually quite feasible to do. It takes less than a day, okay? So I had a pleasure of explaining you our latest work on RFX. It's well documented. You can try it yourself, and we would like to acknowledge the work from Dr. Robert Sherman and Brian I. Everman from Craig Venter Institute. And we are also grateful to Stanford, Professor Russ Altman, who funded us originally through NIH subgrant, and to SFSU COSI for Computing for Life Sciences Center. I'm sure you have a lot of questions now. Please send them to me. Please try RFX and give us some feedback. We hope to publish it soon. We have even some new results. We are preparing it for upcoming ICPR conference. For some further thinking for you is explainability important for you? What are you doing with AI? Are you using it? Are you doing it as a practitioner, developer, or you're legally liable for it? How important do you think is for real users who are not experts? Then, do we need to develop new explainable algorithms, or we try to explain black boxes with certain dubious ability to explain them? That's really questionable. Can we use, and some people are already doing it, some people are using random forest to audit deep learning. Deep learning is black box, maybe a bit more accurate, although I'll tell you they're really close in accuracy. Then you can run random forest if it's possible to do it and get some idea if the features that random forest or RFX nominates as best ranked features are explainable. That can help you kind of build some confidence in your black box. Should we as a research community enforce and require that all published AI systems be explainable? A lot of people are discussing that because of the fiascos in some seemingly correct AI decisions made due to all wrong reasons. But the key question pointed out to me by some authors of the paper, which I quoted in these slides, what if we explain the AI system? How will the company make money? They invest a lot of money, you explain it in one page. How will they make money? Well, looks like most of their money comes from the data, not from AI algorithms. So that's something to be thought of. And once we explain those algorithms, are we opening them up for hacking and defeat? I don't know what to tell you, but I really feel we should explain them. Maybe like in open source, if everything is open, people try to hack it, but people also correct the hacks. So as you know, open source today is very reliable, more than black box code, because the hacker can be unhacked too. And ultimately, can we extend the RFX concept to non-RFX AI? And I think we can, as long as there is some way to rank the features. So this is what I have to say. Again, this was part 2 in a separate file. If you have any questions, let us know. I provided all the references. Please try RFX, send us comments, use it. And I think even by using subset of RFX features, you will see that you can drastically reduce the complexity of your classification algorithms. Thank you very much for your attention. It's been a pleasure. I'm really sorry I could not meet all of you in person, but maybe I will do in the future. Thank you very much.